Good morning, everybody, and welcome to this last session before lunch of PyCon AU 2018. Our next speaker is Brianna Laugher, and she will be speaking to us about the case of the mysteriously high system load. Please make her feel welcome.
Good morning. My name is Brianna, and I work at Planet Innovation. Today, I'm here to tell you a tale. If I can progress slides. It is a seemingly normal day in July 2017 when Detective Plum Bago arrives at work. Plum is a lead private investigator for mysterious software behaviour. She's been working on a piece of software, a Python web application, which does a lot of background tasks. It uses Celery for queuing and managing the background tasks. She checks in on the application running on the staging server, expecting to see that the tasks are ticking along as they normally do. But instead, she finds a very unhappy server. The system load is through the roof. The server is choking on background tasks rather than completing them. The database is in overtime and the web responses are crawling. It's a crisis. Somehow the system, which has previously seemed to be working okay, is now choking under that same workload. So let me pause here to give you some context. First, I want to introduce Jerry. Jerry is a time-lapse incubator for treatments like IVF. As an incubator, it has controls for temperature, CO2 and humidity. While embryos develop over 3 to 5 days, Jerry creates time-lapse videos which allows embryologists to review the development without disturbing them by opening the chamber. The software is written in Python and C++. Secondly, we have Jerry Connect, and this is our server application in question. It's an on-premises web application for remote viewing and assessment of embryos. One patient will typically have multiple embryos treated at the same time, and this application helps embryologists choose the most viable embryos for transfer or freezing. And Jerry Connect is mostly written in Python and JavaScript. Let's watch a snippet of video so that you have an idea of what I'm talking about. This video is time-lapsed, so although the video content is 2.5 minutes long, the real length of time that's passed is actually about 5 days. And we're just watching a little 40-second snippet, which is about 33 hours of development. And we can see some cells dividing. Now, one Jerry instrument has 6 chambers, and each chamber supports up to 16 embryos at once. These would be different embryos from the same patient. And then for each embryo, we take time-lapse footage at up to 11 different focus levels or slices. So what are these slices? These images are taken at the same point in time from the same embryo, but at different focus levels. They show that the embryo isn't a 2D thing, that there is actually useful information embryologists can get by looking at the top or the bottom of an embryo. And Jerry Connect, as I mentioned, is an on-premises server. So we'll have this computer sitting somewhere where it can be connected to the Jerry instruments in the lab, and we support a maximum of 5 Jerrys for one server. And then, of course, we also need to connect to the office network so embryologists back at their desk can be reviewing the videos. While the Jerrys are taking time-lapse images, every half an hour, the images are encoded into a new video segment, which Jerry will then tell Jerry Connect about. And based on the information that Jerry passes to Jerry Connect can then go and download that new segment and append it to its video file. Our download video task has 3 components. First of all, we need to download and parse the segment metadata. Second, we need to actually download that video segment. And thirdly, we need to update the database. So how much data are we talking about? Well, if we have 5 Jerrys, and they all have 6 chambers full, and each chamber has 16 embryos present, and the Jerrys are configured to use 11 slices, that's going to be 5,280 separate videos and separate download tasks. Each video segment is about half a megabyte, so that adds up to 2,640 megabytes that Jerry Connect needs to be able to download every half an hour. And if Jerry Connect can't keep up with this workload and complete all those downloads in 30 minutes, the queue will build up and embryologists will be missing the latest video. Inside the server, we rely on a lot of open source software. We have the Linux operating system, a web server, an app server, some web frameworks, and finally our code, which is the green items at the top. We use RabbitMQ, which is a messaging queue, and that's our backend for Celery, which is our task queue library. And Postgres is our database system. So now that we have an idea of what we're dealing with, let's jump back into Plum's investigation. The first thing that Plum did was some quick recon to see if there was any witnesses, that is to say, useful logs. And the trouble is, logs are terrible witnesses to performance problems. If there's an error in the logic of your application, there's a good chance you'll see that in a log. But if something just runs slower than it should, in the best case, the calling application will log the time that it took, but it still won't be able to tell you why it was so slow. So Plum didn't find anything useful. Then Plum turned to assemble a team of top detectives. They were developers and managers, QA people and systems analysts who knew the Jerry and Jerry Connect products inside out. And they all had theories. In fact, Plum could barely finish describing the crime before hearing about their pet suspects. One idea was to introduce a database replica. Maybe move some services into Docker for autoscaling. Perhaps we should change the streaming chunk size when we download the videos. Maybe we should stop using HTTPS to avoid the overhead of encryption. We should probably examine the overhead from Celery and RabbitMQ. And maybe analyse the network to identify any bottlenecks. Or maybe we should just throw away the whole implementation and rewrite it using rsync. Plum took note of all the theories, but she insisted that before arresting anyone, before making any fixes, there had to be evidence. They needed to have metrics. Metrics are data to help us understand what's happening behind the scenes over time. For example, when Plum's application hit crisis time, there was no easy way to know how fast the system was working through the download queue. All Plum's team had to work with was logs. Now, it's rather painful to graph data from logs by hand parsing it, but it can be done. Here's a graph of the queue backlog from the pre-metrics time when the staging server was scaled back to just 2 Jerrys. It shows that the queue peaks at just over 500 tasks, and overall it takes about 22 minutes to complete. At this time, the system could process around 70 download tasks a minute. Obviously, this system wouldn't be able to support more than 2 Jerrys because then the queue would take more than 30 minutes to clear. So one of the key performance metrics for this application is how fast the system can work through that download queue. When looking at server performance, one of the first programs you might look at is top, or htop, which is shown here. And one of the main things that top will tell you is the current system load, circled in red. This load average is a key concept to understand. It refers to how much processors are having to wait before having access to a CPU. This screenshot is from the staging server, which has 6 cores, and we can see that the load is more than 6, it's 9.12. And unsurprisingly, all the CPUs are maxing out. Now, the Jerry Connect server has 6 cores, and during the crisis period, it was regularly reaching loads of 30. So it was really struggling. Now, top is a good starting point, but it doesn't help us dig into what are those processes actually doing or how their values change over time. Many people will be familiar with the term monitoring, and software like Nagios, which is kind of like capturing the statistics from top every minute and then graphing it over time. But to look inside our application, we need to be able to add application metrics. We need to add metrics about specific behaviour within our system, which is to say instrument the system, to give the system as a whole the probability of observability. So that sounds good, but how do we actually do it? In 2011, Etsy released a package called StatsD, and it's a way of sending metrics from your application with a low overhead. And StatsD has been very influential. It goes hand in hand with applications like Graphite. Graphite is a Python app, it uses Twisted and Django, and it was released as open source in 2008. It's very commonly used with StatsD, and it also plugs into a bunch of prettier and more modern graphing front ends. So we used a Docker image to run Graphite and StatsD, and this worked really well. We also used a package called collectd to gather lots of system-level stats from Linux, like network traffic and disk usage. There's lots of plugins for collectd. For example, we used some for RabbitMQ and Postgres. The Postgres one is particularly good because you can collect metrics from custom queries, which is really getting application metrics without even modifying your application code. And Celery StatsD is a Python library which will also get all the timing and success failure metrics from your Celery tasks. Here's an example of a dashboard which you can define in Graphite. This one's showing some system level metrics like CPU usage, system load, memory usage, network traffic, and number of web requests. But we still need to add those application metrics to find the source of our performance problems. So how difficult is it to actually add metrics to your Python application? On the Python side, it's a matter of using pip or pipenv to install the statsd package. And then in a module where there's a function, you want to record the time it takes each time it gets executed. We just need to initialize the client by telling it where to send the metrics to localhost port 8125. And then it's literally a one-line decorator above the function we want to measure, and we just specify the name that we want for that metric. There's a couple of different types of metrics. So a timer is one kind, but another kind is a counter, which we can modify by calling statsd.incr or increment. And here we used counters to record how often we got different types of responses when Jerry Connect was trying to download metadata. If we found that we got a lot of 404s, it would probably indicate a problem on the Jerry side. If we get a 304, it means the content hasn't changed, and probably we're not going to download anything after that. So to come back to our task has these three components, and we can now record the time for each of these three parts as well as the task as a whole. So where are we going to find our problem? First of all, for the overall task time, this graph shows us that it's typically taking around 4 to 6 seconds to complete. The first step is downloading and parsing the metadata. So this graph is showing that that is taking 50 to 150 milliseconds. So it doesn't look like that this is the problem. The second part is actually downloading the video segment. And this graph is showing it's taking around 100 to 200 milliseconds. So that's also not that slow. Our total time was around 5,500 milliseconds. We've accounted for maybe 300 milliseconds here. So that means it's actually our database update function which is slow. This is taking 3.5 to 5.5 seconds to update to a locally running database. So having laid the groundwork to gather evidence and profile some suspects, it's now time for Plum's team to interrogate the suspects and start making some arrests. And I do use the plural intentionally. Software criminals rarely travel alone. They may not be coordinated, but they are opportunistic. Now, the first suspect we just identified was this database update function. So let's take a closer look at what it is actually doing. As well as keeping track of how much video we have downloaded for each individual video, we also need to track for each chamber how much video we will let the front end show to the user is available to play. We want the embryologist to see a consistent length of video for all the different videos in one chamber. So while a Jerry is encoding each video individually and Jerry Connect is downloading each one individually, we need to keep updating this chamber value. And this update was happening in this database update function, which is running in every download task. And so for 175 times out of 176, the value wouldn't actually change. It's only on this last video, the 176th time, that the value is actually different. And this calculation is not cheap. So we thought about, what do we want to do with this calculation? First thing would be to think, can we optimize this query? Analyze what Postgres is doing, add some more database indexes, and so on. But doing no work is always better than doing optimized work. So we realized that this calculation didn't need to be up to the second accurate. It didn't need to be run in every single download task just in case the value had changed. So we moved it out of the download task into a new independent task, which could do a kind of sweep and just check for any sessions that had changed every 2 minutes. And this expensive function went from being run hundreds of times a minute to at most a dozen times. We saw with this graph before that the queue backlog would be up to 500 tasks and take around 22 minutes to clear. So after we made this change to move the calculation into a separate task, our queue backlog looked like this. And you may not be able to see very much there because the graph shows extremely narrow spikes. There is no sustained backlog. We can now complete video downloads basically as fast as the requests come in. The queue backlog is 0 most of the time, which is how you want your queue to be. But given that we were used to seeing the queue peak at 500 tasks, when I first saw this graph, I thought there must be a mistake. Like we must be graphing the wrong thing or we've missed something, but there was actually no mistake. We could previously only do about 70 tasks a minute, and now we can do 400. Culprit number 2 was configuration. We were lucky to have someone you might call a Sherlock of Postgres on our team, and I highly recommend looking for Curtis Maloney's talk from Friday on Postgres indexing. We did add some indexes in Postgres and also changed some of the settings to be more appropriate for a high write load as opposed to the default values, which are more suited to a high read load. Now with Celery, what had happened was a few months earlier, we had ported all the background tasks from a different task library to Celery. Because we were new to Celery, we didn't really know what appropriate settings would be, so we just kept the similar settings to the old library, which was running 24 processes. And we have 6 cores, and Celery didn't really like this at all. And we changed the value from 24 to 5, and that single change basically halved the system load by itself. So with the arrest warrants prepared, it was time for Plum to conclude the case. Plum had been collecting graphs, so she could show evidence that during her investigation, the system load had gone from 30 for 2 syncing Jerrys and the ideal load of 6 is shown on a yellow line on this graph, at the initial crisis time, to loads of around 10 for 2 Jerrys, and then finally progress to loads of 6 or under for 5 Jerrys. Plum called her detective team together again and presented her case, which is to say, showed off her graphs. And the response from the team was total agreement. Everyone was aligned. Despite all the different pet theories that had been raised initially, everyone was convinced that the culprits were indeed guilty and the crime had been arrested. So Plum was very happy to say the least. The case of the mysteriously high system load was closed. So some takeaways for handling system performance problems. It's really important to explore the problem space before the solution space. If you don't understand the problem, you can't have the confidence that your solution is actually a solution. So take the time to fully explore and understand the problem before you start to think about solutions. With our detective team suggesting all kinds of unusual fixes, it kind of reveals more about them than it does about the problem. Next, make sure you check or double check your configuration. The best piece of software in the world could be terrible for you if you don't have it configured appropriately for your use case. And this is something that tends to come from experience or from trial and error. But if you're doing trial and error, then you're going to need metrics to know if you're actually improving things. Thirdly, logs are poor witnesses to performance problems. They don't cut it. You need metrics. And you need to add application metrics now to solve performance problems or even recognize performance problems later. You need to know what normal for your system looks like to be able to interpret what's happening when things go awry. And finally, I encourage you to have empathy for your future self and for your past self, because debugging is like being the detective in a crime movie where you're also the murderer. If you're interested in learning more about Planet Innovation, please come and talk to me or Adrian Higgins. And otherwise, thank you for your time.
Thank you very much, Brianna. Do we have any questions? Over there.
Hey, thanks for that. So you said that basically one day you came in and it was just in a bad state. Is that really true, or is it just that one day you discovered that it was in a bad state? Like, what was the tipping point that it went from this is working fine and there's no problem to we have a significant problem?
Yeah, great question. So we were working on adding new features that necessitated adding more background tasks, which meant that the system being overloaded became very visible. Another factor is that during the same period we had been rewriting how the Jerry was doing video encoding. So there was kind of a period where we weren't able to have systems, the staging server, syncing data to see that things looked okay. And then we finally kind of converged things back together and added this extra work, and then suddenly things were not okay anymore.
Yeah, just leading on from that, have you considered adding alerting to the metrics you're collecting so that next time you find out before your customer does?
Yes, great question. So being an on-premises application, you have to do things a little bit differently to if you're working in the cloud. And with our application, there isn't necessarily an IT team even on staff. They might have outsourced their IT. So it's a great idea, but it's a kind of a matter for our client to decide if that's important enough for them So we basically have these metric systems like Graphite available, and we have like options for them to be turned on by service people, but they're not turned on in the default case because there isn't someone there to actually look at them.
Are there any other questions?
Hey, by putting your metric collection directly in your functions like that, could a problem with the collection infrastructure lead to further performance bottlenecks?
Yep, so as I mentioned, we're using StatsD, and that's based on when you send that metric from your application, it's sending a UDP packet. UDP is different to TCP, where you don't have to acknowledge that the packet was received. It's basically fire and forget. So our application is firing these metrics off into the ether, and whether or not anyone receives them and actually reads them, it doesn't actually care about. So I didn't observe that it had a performance problem for us.
Are there any more questions? I guess not. Please. Oh, we got one back here. Yep.
When you were actually trying to figure out what the issue is, did you ever think about just throwing more hardware at it? And what stopped you from going that way?
That's a great question. We absolutely did think about that. So when we had our initial meeting, it's kind of what I talked about, exploring the problem space. So, you know, we don't need to assume that it actually will be a software fix. And so our system had this set configuration with 6 cores, and we did consider that maybe we'll need to change the configuration, add another 6 cores, and we even ordered the hardware to do that, so that we could try it out internally if that was going to be necessary. Doing development in this kind of device style means that you really want to keep the number of hardware configurations you have low, because the more combinations there are, the more testing you have to do. And so the idea of having to roll out CPU updates to every customer was not our favourite idea, but it was on the table. So we had the meeting, and you know, that was one of the options, and we had that as a backup option, but we thought we can spend a little bit of time exploring if there's optimizations we can make in software. And we hadn't really focused on optimizing the workload. Like, there was some pretty low-hanging fruit that we were able to pick off. So I think it's good in the end that we didn't have to go the hardware route, but it was definitely on the table.
I think we have time for one more. I guess not. Please thank Brianna again.